we are presenting the simplest approximation for the exchange and correlation energy. And this is called the local density approximation, or LDA. And it was proposed by Kohn-Sham in order to implement their method. Actually, at the beginning, they didn't thought it could be useful at all because the approximation is quite crude. However, this approximation it's used nowadays in different ab initio calculations. So the exchange and correlation can be written in terms of this exchange and correlation energy per particle in this way. And the exchange and correlation energy per particle that we are going to consider in this within this LDA approximation is the one of the infinite uniform electron gas with density n. Of course, the systems that we are going to analyze, solids, molecules, atoms, they don't have the density, electronic density is not going to be uniform. Of course, it's going to change from one point to the other. And actually, the gradients of the density might be very high, very close to the nucleus. So that's why a priori it seems strange that an approximation which is based on the uniform electron gas approximation could be so useful. So in this LDA, the exchange and correlation energy per particle of an inhomogeneous system at special point R, where the density at this point is nr, is approximated as the exchange and correlation energy per particle of the uniform electron gas of the same density. So we are going to use the expression for the exchange and correlation energy for the uniform electron gas in terms of the density, and you're going to substitute this density with the density you have at this point R. And then you are doing this integration here, and you can calculate the exchange and correlation energy functional within the LDA approximation. But for that, of course, you need an expression for this exchange and correlation energy per particle for the uniform electron gas. And what is that? So you can split the exchange and correlation energy for the uniform electron gas in two terms here. Another term associated with the exchange contribution and another term associated to the correlation energy. Okay, first we're going to analyze the exchange contribution. Actually, if you go to the definition of the exchange energy, this is basically the average of the electron-electron potential energy when considering the Kohn-Sham wave function minus the Hartree energy. But with considering the uniform electron gas within the Kohn-Sham model, where we do have this fictitious system with non-interacting electrons, the wave functions for that system is going to be the Slater determinant, which is built with plane waves. And actually, that Slater determinant were the same as the one we used for the Hartree-Fock model. So within the Hartree-Fock approximation, actually, we already calculated the exchange energy. And this is the exchange energy we had for the Hartree-Fock approximation in terms as a function of the electronic density. As in this case, the Kohn-Sham wave function is going to be the same wave function as we do have in the Hartree-Fock approximation for that uniform and homogeneous electron gas. The LDA exchange function is going to be the same as the one we derived for the Hartree-Fock approximation. So we already have the exchange contribution for the energy per particle. And that's the one we are going to use in order to calculate the exchange and correlation energy functional. But there is another one which is remaining, another term which is remaining, which is the correlation energy for the uniform electron gas. And this is much tougher because there is no analytic calculation for that. So what can we do? This quantity actually has been obtained numerically for a number of densities using accurate quantum Monte Carlo calculations. And after these calculations were done, it has been fitted to a parametrized function of density, satisfying the high density and low density expressions. Actually, these high density and low density expressions were already analyzed, were already presented when we analyzed the uniform electron gas. And as you can see here, we are using, instead of the density, we are using another parameter, which is an RS parameter. This RS parameter basically is the average interelectronic distance, and of course it's related with the electronic density in this way, as we already saw when we analyzed the uniform electron gas. So having the parameterization in terms of RS or in terms of the electronic density is completely equivalent. And of course, then the kind of parameterizations that has been proposed are actually different. There are different parameterizations. So here I'm going to present you just one of the parameterizations, which actually is the one which is nowadays most used in the calculations, in the LDA calculation. This parameterization is the Purdue 1 parameterization, which is also called PW92 parameterization, and it was presented by Purdue and 1 in this reference here in 1992. And here is how this parameterization in terms of RS looks like. So here we do have the correlation energy parameterization in terms of RS, which is equivalent of having it in terms of the density. And as you can see here, there are many different fitting parameters, and actually the value of these parameters, you can see them in this reference here. So this is the Purdue 192 parameterization, the parameterization for the LDA approximation that nowadays is most commonly used in the avenue calculations, avenue DFT calculations within the LDA approximation. So here we have presented the first and simplest approximation for the exchange and correlation energy, which is the local density approximation, which of course is an approximation that's quite commonly used in nowadays ab initio calculations. And once we have these exchange and correlation energy function, then we can go to the constant method, and we can merge that parameterizations there and calculate the constant equations considering the external potentials that we do have. So you can calculate either the densities for atoms, molecules, or solids.